Okay, there we are. This time we're going to do, where were we before? Convolution to the forward, convolution reverse, and yeah, I think convolution derivative. Is that it? Yeah, that's where I was before. Convolution get derivatives. So we're going to do the same thing we did last time and just copy and paste it and try to modify it. Okay. Convolution get derivatives is mostly the same thing, so there shouldn't be too many huge differences. So it should be easy. It should be. I'm not entirely sure. Okay, reverse that. Global, not global, device. Double underscore device. Okay, I think I remember this. What did we call this before? Yeah, index map, convolution to the add. Okay. Okay, not type null unit. Yeah, we have to change the name, so type null to CUDA null. Okay, what is that? Incomplete type is not allowed. Yeah, whatever. CUDA null, type null. It'll be fine. Filter. Type null unit, sum. Okay, I'm pretty sure there's nothing here we need to change. So it's an external function. There's no real for loop. For n equal index width. Whoa, what is that? Oh, okay. Before we're going vertically because we are doing a convolution, but here we're not doing a convolution. We're going to one single pixel of the filter, and then going to every single pixel of the source that this particular pixel of the filter has affected. Normally we sum each when we're doing a convolution. We take a list of pixels in the source and we sum up the corresponding pixel in the filter by it. But here we're just taking one pixel in the filter and then summing up every pixel that this particular pixel has touched. Okay, there's a result, there's a source, but it only matters for the source. We don't need to know the result, or do we? Yeah, it's the source. Okay, now for this part right here, second part. I don't want to have to redo everything, so let us copy everything. Hopefully this is not too different. Hopefully. If it is, we'll make the changes necessary, but I'm pretty sure it's mostly the same thing. Okay, for I, for J, for K, kernel map convolution filter add. So not too many changes. Okay, result length, source length, I and J. Okay, let's see what we're missing. Result length, source length. There's an I, there's a J, and there's a K. Okay, so we have to know which one is which. I, J, K in order. So it's X, Y, and Z. That's the first step. We're using all three of the dimensions. X, Y, and Z as I, J, and K. We haven't decided what we're going to do for each one yet, but it should be the same thing as before. Okay, I, J, source length, result length, but we have to make sure which one it is. Okay, source count, result count, filter length. Source count, result count, and filter length. Result count, J filter length, and K is filter length. Okay, so everything is just copy and paste directly from here. Source count, result count, filter length. Okay, but how about the count? Index map, result count. So everything in order plus a K. What is K? Oh wait, no. This we figure out later. We're not going to use the function name. Okay, so we don't need that one. So we don't need that. Okay, so now we need to figure out what is what. Okay, so we just copy and paste. Oh, we do need to figure it out. What am I doing? I thought we didn't need it, but we do need it. Okay, so there's no sum. Now I need to figure out what means what. Copy the name. Now we need to figure out what exactly we're doing. Result. This is that. Source. This is that. Filter. This is that. Index width. We know what this is. Index height. Keep everything as close as possible just so we don't get lost. Result length. That is result index. But what is result index? We need to figure this out. What is result index? This is going to be complicated. Or maybe not. Result length index is time j. Result length times j. So what is j? Okay. Oh, we inside the loop, so I don't think things change very much. For j equal result count. Why is there a loop here? Oh, there's not. Oh, there has to be a loop somewhere, but I'm not sure why. Oh, we don't need a loop. Oh. Okay, so why do I have a loop? I separate this function right here, but we don't actually need a loop anywhere. So why is this here anyway? Oh my god, this is complicated. Let me just try and figure out what I was doing before. Oh, there is no loop. There is no loop. Oh, there's no loop, there's no sum. We just call the function directly. So why separate? The reason I separate in a separate function is because it's just too complicated to figure out it. We have to do I times j. Oh, this is complicated. Now I need to figure out what I was doing before. We can't just copy it directly. Or maybe we can. We just have to make a few changes. Instead of I, j, let's just get x and y. That's why I didn't want to change it. Y. No, for x, let's just change the name of the variables because otherwise I'm just going to confuse myself here. X, I equal x, j equal y. Okay, I equal x. The problem is that I got into a habit of adding a third function like add and subtract, and I just carried the same habit down here without really thinking about it. Okay, sum filter equals, yep, there's no loop. That's why. Okay, so I don't need all this. I don't need a second function. I mean a third function. Result source filter index map result index. Do I need a result index? Oh. Okay, so that's why I have to calculate everything. Okay, so just convert everything, take everything that up here and send it all the way down here. Just copy and paste. Just copy and paste. And then we'll figure out what we're missing later. We use sum xy index counter. Let's copy this somewhere here. Okay, result index equals what? Result index equals result length times j. J times result length. J times result length. Everything the same. I times filter length. No. Equal J times source count. Oh, I'm confusing myself here. Okay. Now I need to figure out what I'm doing because wow. That's a lot of stuff here. Okay. Where am I? Oh, wait. I'm in here. I'm in the wrong place. Okay, J. times, we're copying right everything as it does here. Okay, we need to figure out exactly what we're supposed to be doing. So step one, get our location, get which pick for I equals, we're going to every single filter. There's width times height of filters. So k equals the specific filter that we in. For I equal j, no, the specific pixel inside that particular filter. For I, j, this tells us which filter we're in, and k equals that particular filter. Now we need to know the address of that filter. So j times source count plus I times filter length equals filter index. We don't need filter jump. Okay, this tells us where we are. Now, for that particular filter, okay, not filter offset, filter index, not, okay, I need to figure out what filter offset means. Filter offset times index width. Why is that there? I can't remember why I put that there. Okay, we have to reverse engineer what we just did. Filter offset times index width. Filter offset is the specific, the y value in, no, filter offset is the y value, is the k, which specific pixel in the filter. That's the y value times index width. Oh, that gives us the specific, the row, not the row, the column. The specific j equals the specific column. That's what y is. Y equals the specific column, which is k. K times index width. Okay, y equals k times index width. That gives us a specific column into the index map. Okay, y plus x equals, we're traversing the entire column, and then adding up the values of, we're doing the convolution with the convolution for that particular pixel, source that pixel. No, not I. Oh wait, it's not I, it's x. Oh, we're confusing ourselves here. It's not I, it's x. And the index map convolution to the add. Okay, right. Actually, not that we need this, but it's x. Let's just make sure not to confuse ourselves. Okay, so traversing the entire column, doing the convolution for that particular pixel, and filter index plus k gives us that particular pixel in that particular filter. All right. Oh, it's not that difficult. Although, yeah, I messed that one up. It's y. K is block.idx dot z. So this gives us our location. Make sure that we didn't overload. Filter length. Is it filter length or filter count? Yeah, it's filter length. Okay, now we need to know which pixel we're in. We know which filter that we're in. So we do the multiplication as usual, and then we'll multiply that by filter length. This gives us the start pixel of the particular filter that we're operating in. And then down here we do the operation on that particular pixel of the filter. Does that count? Why is that counted? No, the counter is for just so we can divide, because you cannot take the sum because there's too many of them. So not that difficult. Let's just make sure we didn't miss anything. Convolution to the add. Everything is the same except for we replace ij with x and y. Okay, so this is perfect. Here we just do the loop and we call everything the same as usual. I times filter length, j times filter length, result length. And did I miss anything? Yeah, I probably missed something, but so far it looks really, really good. Convolution get derivatives. Okay. Convolution derivatives. CUDA and whoa. Oh. Okay, this is gonna get really painful very soon. Very, very soon, because I cannot forget the whoa. How many times did I forget? Convolution to the forward. I completely type. Wow. Oh my god, I forgot to convert everything. I really need to get rid of this because otherwise I'm going to just confuse myself. Okay, I just need to remove the type, convert a type neural unit to CUDA neural unit. I should probably just refactor. Yeah, I haven't learned how to do that yet. Let's do it manually. Normally you just do a find and replace, but I don't feel like doing that right now. Doing it manually just helps you make sure that you didn't miss anything. Convolution to the get derivatives. Oh, get rid of that. Yep. Convolution to the add. Get rid of that. Kernel array index map convolution to the reverse. Get rid of that. CUDA neural unit. Type neural unit. Okay. Now let's do the finalize the conversion. Let's get rid of this. Everything should be exactly the same as before. Okay, unless I missed something. No. Okay. Just make sure we didn't miss anything. Okay, for I, source count, result count, filter length. And now we're going to do the final stage of the kernel conversions, which is the third dimension. Here we have 16 by 16, but that doesn't add up to 12, to 512. So we do 8 times, no, 8, no. I'm not sure if it's necessary to do it that way, but I've always done it that way. So in case there's a better way to do it, I don't know what it is. So, okay. So let's just make sure we got everything here. Source, result, filter length. Source count, result count, filter length. Filter length. Okay, X, Y, and Z. Okay, learning how to do CUDA here. Whoa, whoa, what I miss? Oh, wait. Just make sure everything lines up. X, Y, and Z. Let's just ignore that for now, just because we might need to do corrections later. Evolution. Oh, wait, what am I doing? Whoa. Oh. I didn't change the name. What am I doing? Kernel convolution get derivatives. Convolution to the get derivatives. I didn't change the name. Convolution index map convolution to the get derivatives. Kernel. It's a long name, but doesn't really change anything. Just to be, we're just trying to be. Oh, get rid of that. No, convolution to the get derivatives. Okay, so everything lines up. Let's not forget the most important part. We have to call synchronize. Otherwise, we have trouble. Return synchronize. Okay, now we need to make sure that we didn't miss anything. Oh, filter count. Result source filter index result source filter. Let's get rid of this. We don't need this anymore. If index map not equal index. Okay, we need to make sure that things here line up. Okay, so just copy and paste everything. Make sure it all lines up. I'm pretty sure it does, but let's just double check. Index map, result source filter, index map. Oh, slight cosmetic problem. Or index map equals 0. That's a really stupid mistake. Result source filter, index map. Is there an output? Oh, no, there's no output. I don't think. No, convolution doesn't require output. Okay, result map, result source filter. Yeah, you have to copy this. Index map. Index map, result source filter. Go show to the forward. Index map. We show to the value. Result source output. Oh, it's a slight oversight. We need to check everything, make sure that everything lines up. Result source index map pulling to the forward. And source index map copy to the. Okay. Index map to the computation to the forward. Get derivative ijk xyz. Results is it source? Oh. Source result. Yeah, source result. Normally I get it, I put it in a different order, but okay, result source I, J, and K. K is a particular pixel. This is the start. Just make sure we had everything right. Index map. Okay, it's all good. And it's all good. We're getting close. We're getting close. Okay, there's a one or two more to do, but there should be. Oh, momentum at a grad. Oh, there's a lot more to do. Okay, next we're gonna do matrix. That should be simple enough. Matrix, just to remind you, is the fully connected layer. Okay, CUDA neural. Let's copy everything here. CUDA neural, CUDA neural, CUDA neural weights. Okay, CUDA neural also. Did I remember? Oh, I did not remember that. CUDA neural array. Yeah, CUDA neural array. Okay, kernel matrix forward. Kernel array matrix forward. Kernel array matrix forward is I'm forgetting a few things. Just copy everything is exactly the same as we should. Okay, for I, just to remind you here we cannot do a two-dimensional filter, or two-dimensional kernel, it's because there's a relationship between all these pixels in this loop right here. So we can only do a one-dimensional kernel. Okay, fortunately, this is what we have here. Okay, threads per block. Now, what do we put here? Result.array length, yeah, same as before. And result source, result length. Oh, so we don't need to change anything. Oh, we don't need to change much. Okay, cut and paste. Okay, we need so IJK. We need to copy IJK. IJ. That's just for cosmetic reasons, but I like to keep them lined up like this, just in case I need to put something here. But I don't need to put anything here, so I will do. For I equal length. Length is just result length. Okay, for I equal length, sum equals source. Oh, wait, no, there's no length. Ah, result length. There are two different lengths. Result length, unsigned long, source length. Okay, there are two different lengths, so we need to make sure. Okay, if I less than result length. Okay, k equals source length, because we're dealing with two-dimensional. Oh, there's a weight. Oh, so we can't just do it normally. Weights will be 8. We're trying to do everything the right way, but okay, so we have source, result, source, weights. So the reason I put result first, just to keep everything lined up, because you can put it in any order, but just to keep everything consistent so that I don't get lost. Okay, no, it cannot be. Oh, that's what we have to do. This has to go down here because we're doing J. I is reserved for source, J is reserved for result. The X one is always the first one, so that's why it has to be X. The J has to be X instead of Y, because when we do the kernel, it always we cannot, if we only have one, it always does the X one instead of the Y. Okay, for I equals source length, source dot I equals weights dot k plus I. Okay, sum. Oh wait, for I equals result, I equals 0. Why is it complaining? Of course it's initialized. It's not right here. It's just complaining about something. But there's no error here. Okay, for I equals result, k plus I, result dot j equals sum. Okay, that's the first part. And now we get rid of this. And let's make sure we didn't miss anything. Yep, everything's fine. And we get rid of this. It's complaining down here, but there's no error. And everything's fine. Next. Okay, is there an error anywhere? Just make sure everything is in the right place. Yep. So we converted a matrix forward, this function right here, to a kernel version. So we just call a kernel for each pixel in the result, matrix forward. Now we need to do matrix reverse. Let's just copy all this right here, and we have to do some modifications. Matrix reverse. Okay, first thing, we need this to give us a visual verification of where we are exactly. Reverse. First thing is to change the names, just so we don't forget. Oh, ha 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 ha. Let's not forget this. Actually, I made a huge mistakes. I was so sure I got everything right. Turns out I got everything wrong. Just move it down here. Results, source, source, weights. and results length, source length. I was sure I got everything right. Source.array length, but it's wrong. Result data, source data, wait, result, source. Okay. Make sure you didn't miss anything. So far, so good. Yep. Okay, now reverse. It does not work exactly the same, which is why you have to copy and paste here. Okay, first of all, source, it's source.array length in the kernel. In this part, oh wait, this part here is source.array length. Let's just copy and paste everything, just so we don't lose it ourselves here. Okay, first it's source.array length. It did j for I equals source.array length, and all the parameters are still the same. And then now for up here, let's just copy this again. So just so we can see what we're doing. Okay, for I, no. Step one, we need the I. So the loop that we're in is the I loop. Oh, mistake. It's if j less than result length, not for I. Oh God. Okay, is it j times source length? Yeah, that's j is the y value times source length. That gives us the specific column that we're dealing with. No, the specific row that we're dealing with. We're multiplying by a row, not a column. Okay, next step. K equals I. If I less than source length. Oh, source length. Okay, sum equals 0, K equals I for J. We pretty much just copy everything because it's exactly the same thing. We don't need to worry about this. It's exactly the same, just copy and paste. Okay, for result length, just copy and paste, and result length, result data dot j equals weight dot k, k plus equals source length. Source dot I equals sum. Did I forget here? Source dot j, result dot j equals sum, and perfect. Okay, so far so good. This is gonna take a little while. CUDA derivatives for j equals source dot array length, sum equal result times weight, result dot j times weight dot k, k plus source. Now here we're doing a column. Down to we're doing the dot product on a column, not a row. Okay, and the sum result equals sum. So far so good. Perfect. Almost perfect. Threads result array length x blocks per grid, kernel analytics reverse, and there might be an error somewhere, but so far it looks good. If there is, we'll catch it at some point. Result source data. Oh, is it source? Oh, wait. What am I doing? With reverse. This is exactly the same. Kernel array matrix reverse. Kernel array matrix reverse. Everything's all the parameters are the same, except here with source instead of result. Okay, that's why I did it. Align everything up because we need to remember to change x with y, I plus I and j. Okay, I is the x value, j is the y value, and k, yeah, k is the specific index in the weight. Okay, next, we're just going to matrix derivative. That one, just like with convolution, it may be a bit complicated. Just copy the kernel. Okay, step 1. Just copy all the kernel values. Okay, is that 2-dimension? Whoa. Okay. I'm gonna have to think about this real hard. Okay, because now we're going according to each array in the specific to each weight, which is the source length times result length. Okay, the number of weights is the source length times result length. So this part right here has to go. We're doing using a 2-dimensional kernel. Let's just do the kernel first, and then we're going to modify this part down here because it's working in a really different way. Modify the kernel array matrix get derivatives. Not kernel array matrix get derivatives. Oh, let me just copy everything down here, up here, because modifying this one is going to be tedious. Okay, ij, we're just doing everything again. Okay, derivatives, weights. Let's keep the names exactly the same. Derivatives dot k. So what is k? Okay, weights. No, not weights. Derivatives. Okay, derivatives dot k equals result. Oh, do I keep the names the same? No. Yeah, we don't keep the names the same. Deltas. And outputs. Oh, wait, no. Oh. This would confuse me too much. Result. I want to change the names to match what it's supposed to be used for, but I don't feel like doing it. Source. That's not something. We're going to keep all the names exactly the same because otherwise it's just confusing me too much. Why? It doesn't change how everything works. It's just choosing specific names. Because that's the way I like it. So source length, result j times result length if j less than result length. Okay, we need to make sure that's within bounds. Okay, we don't need sum. K, weights. Result with weight equals result dot array data dot j times source dot I. But what is k? Oh wait, there's no loop. No, there's no loop. There is no loop. We don't need a loop. We don't need a loop here. It's just 1 dot j. We actually don't even need k. It's j times source length plus I. Wait, this particular derivative is that particular location. Here the reason we do k equals I and then do this here because we're in a for loop. But if we're doing kernels, this becomes impossible. So that's why you have to get rid of this part right here and do the multiplication. Otherwise, because we can't just. This is supposed to be a shortcut, but we can't use this shortcut here because all the kernels are separate. Kernel array matrix get derivatives. All the individual kernels are separate, so we can't use this trick here. Okay. Now we do the same thing here. No, just copy and paste here. And just make sure that we get everything in the right order. Here we're keeping all the names the same here. Deltas, outputs, derivatives. Okay, 5 and 12, it becomes 16 by 16. Result, not result. Source, source. And wait. Keep the names the same just to save ourselves from having to think about everything. That way we just copy and paste right here. Get rid of I, J, and K. There it is. Yep. Matrix forward, matrix get derivatives. Everything's kept the same. Just copy and paste. We will do this later. Okay, the for loop, 16 by 16. And then, come on. It's making itself difficult. Okay, blocks per grid equals source.array length. Is it source or result? Yeah, source, result down here. Dot array length. Y, X, Y. Kernel array matrix get derivatives. Oy. This is proving more difficult than I thought, but it should be. It's, whoa. Oh, what is it doing? Am I missing something? Oh wait, it's this part right here. It doesn't like it. All this right here. Let's do it right now. CUDA neural. No. CUDA neural. CUDA neural. And CUDA neural. Everything's the same. We can just get rid of this. Let's just wait a few minutes before, just to make sure we didn't miss anything. CUDA matrix get derivatives. This part right here is the same. That's why we keep everything, all the names the same, so we don't have to worry about changing anything. Array source, array length. Transfer block Y, X, Y. Deltas times outputs. We just have to remember to change deltas and outputs, because changing the name is not going to help us much. Just make sure everything is in the right order. Source, result, filter. J times source length. And that's it. Yep, kernel matrix get derivatives. Hopefully we're not missing anything. It should compile, rebuild, and then I'm going to check if it works later. Okay, everything compiled correctly. We're not ready to check it yet, but this is as much code as we can do for now. So that's enough for tonight. I'll see you tomorrow.